Hello everyone. Welcome to the lab of 3TR4 course, Communication Systems. This video is an introductory video that will show you what will you do in the lab for experiment 1 in very detailed way. When you come to the lab, you will find this board, this breadboard. As you look, it has operational amplifier here. This board contains positive supply. This is the last grid here. This is plus 15. The last one is negative 15. And the grounds are the inner one here and the inner one here. So it is plus 15 ground. This is ground and this is minus 15. The op-amp is already connected to V plus and V minus. V minus to leg 4 and V plus to leg 7. For op-amp, how to know the leg number? If you look at op-amps, there is a small notch here. This small notch, you start counting from here. 1, 2, 3, 4, then 5, 6, 7, 8. So this is leg 4 and this is leg 7. You put the notch like this and start counting is this way. So it is connected V plus and connected V minus. This is the input signal from the power supply. Just adjust the power supply. This is the V input. Okay, this is the ground. You could use it as well. First of all, you need to connect the filter circuit shown in the lab PDF. That's the first point that we want to do. So that I already connected it. I'll show it connected to you, but you have to connect it in the lab. If you have the lab PDF, this is the circuit that you have to connect. This is the operational amplifier. As I told you, this is leg 4 connected to V minus, leg 7 V plus. This is connected for you. You have to connect only these 6 components. So V2 should be connected to 10K, then ground, 5.6K to V out, leg 3, 0.1 microfarad to ground, and 1K here, then feedback 0.1 microfarad to 6, which is V out, and 1K to V input. Again, that's the V input here. That's coming from supply. Okay, that's again the V plus, which is 15 volt, and this is the minus 15 volt. Okay, that's the connected circuit. That's the 4 resistors, and this is the 2 capacitors. And this is the point of V out, which comes here to this node. I think it is easy for you to connect this circuit. What we are required to do in this experiment, we are required to input square wave of duty cycle, whatever. We'll choose 20% duty cycle, and see the spectrum in the output compared to the input. In the lectures, you took that if you have a signal, you could make a Fourier transform or a Fourier series if it's periodic and got the frequency response. For example, you took in the lectures that for a periodic signal like this is rectangular wave with pulse tau, repeated every t. You have already passed with this procedure. You have find the Fourier expansion and you plotted the spectrum. This is the same wave we will use. You will use this wave. We'll use frequency of 500 hertz. We'll use duty cycle of 20%. You could change this, but this is the typical values. And this is the input spectrum that we expect. We want to pass this signal through this filter and see what happens to the output signal. This signal, when applies to this low pass filter, what will happen? The low pass frequency signals may remain nearly the same, but higher order frequencies should be attenuated more and more. Since this is not an ideal filter, this is a real filter, so it has no sharp cutoff. In ideal filters, when you plot the frequency response of ideal filter, you just make it like this. It is pass. This is low pass ideal filter. All frequencies here pass. All of them here 0. This is not the real world case. The real case here will be something like that. So the filter passes most of the signal here, then attenuates most of the signal here. That's what we want to see here. What is the filter equation? The filter equation is given. H of S it is equal 1 to 1 over S of omega naught squared plus 1.414 S over omega naught plus 1. Omega naught is given to pi f naught, this is the cutoff frequency, and the S is your frequency, j omega, and omega is your frequency. We already know that when the input is a square wave periodic like this is the input, we expect the output to be like this, discrete output frequencies. When this passes through the low pass filter, so the low pass filter will attenuate each frequency bin here. We'll try to measure this on the oscilloscope and see whether the theoretical part and practical part agrees or not. Okay, so first of all, we have set our frequency, set our low pass frequency filter. We'll try to set this function generator. First of all, this is the frequency. We make sure that is 500.0 Hertz. Amplitude, it is arbitrary. As you know, if you are scaled the amplitude, everything is scaled. I just choose 1 volt peak to peak, but you could make it any value. Offset, I'm not interested in offsets, I'm not interested in DC values, I'm interested in the different frequencies response. I now want the duty again, so I will press shift duty to get the duty. It is 20%, and it's okay. If you want to change it or make it like this, that's okay. So that's my frequency. My frequency generator is ready for the experiment. It goes here, it is connected from down. This is my frequency generator connected to the yellow probe. It is here. So when you open the yellow probe, that's the yellow probe. Let's see it in the scope. Let's stop the wave. That's it. You know that's the duty cycle of 20%. It is up for 20%, then down for 80%. With the peak, that's the scale is 2 volt. So this is nearly half the scale. That's 1 volt. This is 1 volt. What about the second signal? The second signal is taken. This is the green one. It is taken from here, which is leg 6. It is the V out. It is the V out. So it is the low pass filtered signal. Let's run it. As we see, it is filtered signal from the input. You know, if you look carefully, there is no sharp edges. You know, when you make low pass filtering to a signal, the high frequency component are omitted, are set to 0. So the sharp edges, which represent the high frequency component, are out. You know, it is smooth like that. There is no high frequency components. Okay, so that's the time domain. This is the time domain. We input the square wave signal with duty cycle 20%, and we got this signal. Okay, what we are interested now, the frequency response of the input. We make sure that is correct according to what we took in theory, and the frequency response of the output, whether it corresponds to this equation and it's correct or not. How to measure the frequency response using this oscilloscope? We are not interested now in the input or output signal. We could make them off. Just when you press this, it is on. Just when you press this, it's off. To get FFT, it is a math operation. So you just press here. That's a math operation. Then you have the hotkeys here. This is the function. I make FFT of this function. The operator is FFT here. What I make FFT for, it is the source one, the yellow one, which is the input. Then I make for the green one, which is the output. This is the span of the signal. You know, our frequency, fundamental frequency is 500 Hertz or 0.5 kilohertz. So it will repeat every 0.5 kilohertz. So 20 Hertz is too many bits. We make it 10, for example. The center frequency here, it is 0. So this is 5 kilohertz. 5 kilohertz giving 10 bins. 10 bins. That's bin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's okay. That's 10 bins, and that's right. Okay. So why this bin is equal to 0? Why is this bin equal to 0? If we go to the theory, which we took in class, alpha n, which is the amplitude of the bin number n, it is equal a over n pi sine n pi tau over t. Tau over t, it is the duty cycle. Tau over t, it is amount of, look, this is tau. So tau over t, it is the duty cycle. So this goes to 1 over 5. We set the duty cycle to 20%, 1 over 5. So that's sine n pi over 5. When n equal 5, that's sine pi. Sine pi equals 0. So this term equals 0 when n equal 5, n equal 10, n equal 15, n equal 20. That's why we have here 2 0 bins. So that bin 1, 2, 3, 4, then 5 is 0, 6, 7, 8, 9, then 10 equals 0. If we have more span, let's make a bigger span. 0, 0, 0, 0, greater span. Look, 4 pins and 0, 4 pins and 0, 4 pins and 0. And what? It is decaying. This is the spectrum of the input. It is decaying. Why it is decaying? Because if you look here, it is A over n pi. When n increases, what happens? All this term what? Decrease. As n, we make n equal 1, 2, 3, 4, 5, 6, 7, 8, 20, 40, 100. So this term what? Decrease. Okay. We want to make sure that this spectrum is correct. The numbers in this spectrum is actually correct corresponding to this. We want to make sure that this is correct. How to make this? Okay, let's set the span to 10 kilohertz again. We want to take values. We want to take values to make sure that these numbers correspond to the correct spectrum. We don't expect that they will correspond 100%. This is a real system with real noise, with real problems. So we expect that it is 90%. I want numbers to be close to each other. I don't expect them to be 100% equal to each other. Okay. So this is the frequency response. I want now cursors. I want now cursors to choose whether the vertical axes are correct and the horizontal values are correct. If you look here, that's the cursor. That's the cursors. When you press here, you get the cursors. Okay, let's take first the Y cursor. I could change the cursors from here. I'm changing the cursor here. So I get to the peak of the bin and read the value. That's negative 18.75. Write it down. The second bin, negative 13.75 dB. Write it down. Here, negative 17.5. Write it down. Negative 23.75. Try to be accurate as much as you can. But as I told you, it will not be 100% accurate. So that I try to write down the values of maybe the first 4 bins is okay. To make sure that these bins are equal or actually correct to the theoretical ones. Okay. What about the frequency? Are these frequencies okay? Let's choose the cursor, but the X1, the X cursor. The X cursor moves like this. Let's look. Yes, the first bin is 500 Hertz. That's okay. The second bin, 1 kilohertz. Okay. That's perfect. 1.5 kilohertz. Perfect. 200 kilohertz. 2 kilohertz. Perfect. That's the 0 one. 2.5. Perfect. So that's frequency response is okay. I have recorded the amplitudes. I have recorded down the amplitudes. Could I check that these amplitudes really correspond to this wave? That's the problem now. I'm in the lab. I took the record. I have recorded this number, and I want to check if these numbers already correspond to this wave or not. Okay, that's easy. Let's take a paper. Okay, you have some numbers, negative 11.3 dB, negative 16 dB, negative 20 dB, negative 25 dB. We have recorded some numbers. I can't remember them exactly, but we have recorded some numbers. First of all, change them to ordinary numbers. You know, when 20 log x gives us x in dB. We have the dB values. We want what? We want x. So x equal 10 power x in dB over 20. Just go this 20, then log x equal x in dB over 20. So that's it. So we have now the numbers. For the first 4 bins, the 5 bins is 0. We know it is 0. Okay, so we have these numbers now. You could actually get them from the oscilloscope. What is the theoretical numbers? This is the theoretical numbers. Alpha n, a over n pi, sine n pi tau over t. Okay, let's put n equal 1, 2, 3, 4, 5. So for a over 1 pi sine pi n equal 1, tau over t, it is 20%, which is 1 over 5. The second one, a over 2 pi sine 2 pi over 5. A over 3 pi sine 3 pi over 5. A over 4 pi sine 4 pi over 5. And the last one, 5 pi sine 5 pi over 5. What is 5 pi over 5? That's 0. So that's okay. We want this. We want these numbers. If I'm correct, so I will find these numbers proportional. With what proportional value? That's a. So if I have this number, 1 pi, I could calculate 1 pi sine pi over 5, so I could get a. I could substitute with this a here and here and here. If these values are, I won't say 100% equal, but if they are very close to each other, then these values are really proportional. These values are really proportional. What does this value A depends? It depends on the amplitude here in theoretical case, and in practical case it depends on the amplitude of the power supply and depends on any losses in the circuit. Maybe there is some connection errors and something like that. So if I find a single A which matches these numbers, for example, let's take easy numbers, 1, 2, 3, 4, 2A, 4A, 6A, 8A. If A equal half, so that's 1, 2 and 2, 3 and 3, 4 and 4. That's okay. But if this is 7 and this is 9, so there is no A that makes them proportional to each other. So again, these numbers should be proportional. With this value depends on the amplitude of the signal you have chosen in the lab. That's the input frequency. That's the input frequency signal. Okay, if you got these numbers very close to each other, again, don't expect them 100%. Expect them 90%. Expect to get 0.52 and 0.49, for example. You'll have close values to each other. If these numbers are okay with you, then we are ready to complete the spectrum of the output part. These numbers you could calculate them at home. So you could have these numbers ready for you. You just find these numbers and got these numbers in the lab. So while you are in the lab, you know exactly whether you are correct or not. These numbers are already from this formula. You have this formula at home. You could get ready with your numbers, and just when you connect the circuit and measure the values, you could find whether you are correct or not. Okay, that's now we need to use the output spectrum. Okay. This is the spectrum of the input. When we press math, it depends on source 1. I want now source 2, which is the output. Again, we want the span, maybe 10 kilohertz. And again, the center frequency should be 0. This mark is the same as this mark. You are changing for this. Okay, the same pins, but they are a bit attenuated. They are a bit attenuated. Again, we get cursors. We get X cursor. Cursor X, so we check the frequency space. Yes, the frequency is located as we expect. That's 0.5K, that's 1K, that's 1.5K, that's 2K, that's the 0, 1, 2.5K again. But what about the amplitudes? We want the Y cursor again. Again, we have these values, negative 8.1, negative 11, negative 16, negative 25, and that 0 again. Negative 51 or negative 61 is nearly 0. So we again record these numbers down. Having these numbers, okay. So we have now the 3 and the fifth one, it is 0. That's the output. That's the output signal. Okay. What is the theoretical number this should be proportional to? This is the number A over m pi sine m pi tau over t multiplied by the corresponding frequency response. We are now speaking about the output frequency, so we have input frequency multiplied by the frequency response to get the output frequency. Where to get the frequency response is, it is from the PDF. We have here the frequency response. H of S, it is 1 over S over omega naught square plus 1.414 S over omega naught plus 1. It is all given. S equal J omega. It is the frequency that you want to calculate the output at. Where 500 Hertz, 1K, 1.5, 2K, 2.5K. F is cutoff frequency, it is given. So omega naught, 2 pi F naught, that's given. Okay, so we could calculate H of S using MATLAB or even using calculators. So let's first define S. S, it is J multiplied by 2 pi frequency, 2 pi, for example here 2000, take it first 500. So that's S, J, 2 pi, 500. So this is we will speak about the first bin now. What about H? H equal 1 over S over omega naught. I already defined omega naught as 2 pi F naught squared plus 1.414 S over omega naught plus 1. We have omega naught equal 2 pi, okay, that's omega naught with that's H. Okay, H here is magnitude and phase. We are interested only, this oscilloscope here give you only magnitudes. So we are interested in the absolute values. That's 0.995. So the first bin, it is this value. And the frequency response is 0.995. Again, you have all these values. You have tau over t, that's equal 1 over 5. You have n equal 1. So again, you have a multiplied by some constant. For n equal to a over 2 pi sine 2 pi over 5 multiplied by the frequency response of the second bin. How to get it? Again, S equal, instead of 500, it is now 1K. Then H, that's H, we know the absolute values, that's 0.9301. So the second bin, that's here, multiplied by 0.9301. We got this value again. So we have some A's multiplied by some constants that I could calculate, and these values is what I recorded from the oscilloscope. If I'm correct, these values will what? Be proportional. Depends on what? On this value A. What is this value A? Depends on the amplitude of the signal and any attenuation on your circuit. If you are correct, then they will be proportional. If you calculate A from the first equation, or the second equation, or the third equation, or the fourth equation, they will be very near to each other. Not 100%, but will be very near. That's the practical part here, and is the first part of the lab. The second part of the lab is much easier. It is just you open the MATLAB file present in the lab files. When you, let me show you, that's the Y drive on the desktop. Our course is EE3TR4, that's our course. That's the file, filter demo. You'll just open this file, filter demo. I have already opened it. This is the filter demo. Okay, just run it. It will show you a GUI, original speech, and some filtering operation, and filter response. Let's original speech.
It's easy to tell the depth of a well.
That's the original speech. We could make low pass or band pass or high pass and notch filter. What is required? That you press every button, hear clearly what is the sound, and give explanations of why is that. If we press, let's press low pass filter.
It's easy to tell the depth of a well.
That's the original sound.
It's easy to tell the depth of a well.
That's the filtered sound. So we want now, why is that? That's the band pass filter.
It's easy
That's
to
the
tell the
original
depth
one.
of a well.
Then 2 moments. That's the output. If we have a notch filter, we have the same filter signal, but with some whistle sound.
It's easy to tell the depth of a well.
That's the filtered.
It's easy to tell the depth of a well.
There is no whistle. So we want you to explain this. So the first part is the breadboard. Connect the breadboard, adjust this function generator, look at the spectrums for the input and outputs, get your numbers, check that these numbers are proportional for the input and output. The second part is this M file. That's it for experiment 1.